Swayam Prabha. Digital India. Educated India.
This is an in-person talk, once again, which is good. So we have K. Sendil Kumar from NIT Trichy. He's going to present his work on a prediction-based fusion estimator controller for an event-triggered multivariable cyber-physical system. Over to you.
So good afternoon once again. So basically many plans we are sending this information nowadays in a network environment. The network environment may be a wired or a wireless. Irrespective of the medium, because of that lot of challenges which is posed for a control community or even in general. Okay, there are network delay, network constraints like a network delay, pocket issues, okay, even network congestions. Okay, these are all the first one. The next one is the cyber attacks. Okay, there may be a different types of attacks. It's possible and it can corrupt a particular information. And also there are a possibility of, because of everything is connected in a network, there will be a bandwidth limitations. Okay, that is also be posing a problem for a control community. And because of that, everything which is connected in a network type of equipments, naturally what will happen, there may be a power management. Okay, this is a lot of posing a problem for our process community. Why not we can address in the case of network constraints, network control system in this area. That's what our main objective of this presentation. Okay, that's what I simplified whatever it is given in this slide. Okay, so basically, okay, there are different challenges like a suitable design of a suitable communication protocol, the identification of communication delay, packet loss, cyber attacks, etc. Basically, we are addressing more on this presentation, communication delay as well as a packet loss rate. And also there will be a noises which is present. It may be correlated or a uncorrelated type of a system. And there is a limits on a network burdens because of the battery power consumption and other things. Okay. So every time a sensor which is triggered or actuator which is triggered, naturally what will happen, the consumption of battery power, it can also poses a serious problem. So here what we are assuming is, because of this, a lot of literature survey, lot of peoples are working on, okay, on this typical area. Okay, even our groups also we past 5 to 6 years, one of the paper which is published on IIT signal processing and ISA transaction also. So here I can compromise, I can able to tell we have to develop a fusion estimator based control algorithm for the system with multiple sensor with the incorporation of communication constraint. That's the first objective. And a suitable compensation mechanism, we can able to compensate for both delay as well as a packet loss, and also to incorporate solution to the power constraints problem. Okay, that's what we are introducing, like, we are assuming process is fixed. Okay, communication network is also fixed. We are not touching it. Is it possible as a control engineer, we can able to on a controller and estimator level, is it possible can I able to improve this such a system? Okay, that's a basic objective. And finally, we have designed a estimator based feedback controller using orthogonal projections and ALMIs. Okay, the main feature of this work, we have a centralized data fusion, okay, in a multi-sensor framework, okay, and also each sensor having a independent, individual event triggering. Even you can go ahead with a multi-rate also. Okay, there is no need every triggering is fixed on every sensor. You can go ahead, whatever you want. One loop may have 1 second, another loop may have a 10 second or minutes, etc. And we can able to handle various delays, packet loss rate, and various. And also we are the main novelty of this work. We have incorporated a predicted state compensation is used at the estimator whenever the data is not available. Okay, the data is unavailable due to so many reasons. Okay, even a packet can arrive first in, first out. Even it can arrive in a different rate, and also it exceed a certain time. So the naturally what will happen in that scenario, why not we can use our model to compensate for a system. Okay, that's a basic logic which is behind. And the power management, we have incorporated event triggering mechanism. Whenever sensor is reaching a steady state information, okay, steady state region, why we have to utilize? Every time we have to capture the data. Instead of that, we can use a model to supply this data based on past information and other things. That's the main concept which is behind. And I request my research scholar Sendil can continue because he is a contributor. Only we are giving an idea. It's a great opportunity for him.
Good afternoon. So here event trigger mechanism here we are using instead of time sampling triggering techniques. So the same disadvantage of time sampling technique. So even keep on for if we have a 1 millisecond or 1 second of her sensor have to sample in a sense, keep on, it has to measure and it has to send to a estimator or controller. Here we are using some cyber physical network for communication purpose. We are doing many things and through our digital things. So that's why through a cloud we are transferring our data. So this event triggered mechanisms basically are relative error based thing. So here this rho is a rho is a threshold parameter. So by fixing the threshold parameter, we can restrict a number of data, which how many data can transfer from sensor to an estimator or controller through a network channel. So here, in case if you are fixing with rho as 0 in a sense, means 0 or nearby 0 in a sense, we have to many measurements will trigger. So number of out of 10 measurement, we can get 8 measurement. Just an example for this one. And for us, if you are going for larger row in a sense, there is a possibility of like all measurements will trigger together to reach an estimator. So this is what the concept. And here we are using some lambda parameters. Lambda parameters used to develop a model only. Here we are using some random distribution based variables only. It obeys a Bernoulli distribution. So if lambda is 1, since we can assume that we received a measurement, and if it is not, sensor is not pushing any measurement to a controller. So there are some alpha, beta are also used for assigning delay and losses in both the channels, either from sensor to cloud, it has to push a data, from control side to actuator, it has to push a data. That's why beta belongs to controller to actuator, and alpha belongs to sensor to estimator channel. And coming to the centralized fusion, we have multiple sensors for a single system. Here we are assuming MIMO systems, multi-input and multi-output systems. For various measurements, we have each and every sensor will have a simple various even condition, the same event triggering mechanism, but with some differential parameters, so that each and every sensor will push along to this own condition. So later, while receiving estimator, it will compile all those measurements. So here, instead of packetizing each and every measurement here in the sensor and transmitting, we are transmitting all the sensor measurement through various network channels, and we are receiving it from estimator. So this is what my target. And all are vectors here, just written, but all are vectors. We can assume it as vectors. Coming to model, just a generalized state space model, xk is axk plus bk plus gamma k. Gamma is a process noise distribution matrix, and Z is a measurement, actual measurement from sensor. So Y is like the Z measurement, which is transferred through a network channel and which is reached an estimator or control room. So that is what Y. Here, first portion is for on-time arrival. On-time arrival is nothing but in the same sampling instant we are receiving a data, and the next portion is for delayed measurement, and third one. In third, there are two informations. One is for packet loss, and another one is for in case if event is not triggered, then what can be the compensation. This is what. So here we have used if there is no measurement is available to an estimator controller, we are using predicted measurement. Predicted measurements nothing. We are using orthogonal projection here. So based on that, model based prediction technique. So we are using that measurement Z at k given k minus 1. And the sixth equation is just simplified to reduce computation burden. And this from this table we can get if lambda is 1 means in the case sensor measurement is triggered, then there is a possibility of on-time arrival, delay and loss. So first three things, if alpha 1 is 1, then we'll have a ZK, and alpha 2 is 1, then we'll have a delayed measurement, and alpha 1 and 2, if both are 0, then we'll have we don't have any measurement, so that we can use predicted measurement. And the last case is for untriggered event. So that time also we are using predicted measurement only. So this is just a comparison. Below side it has given like packet loss. During this packet loss, we are that red line is predicted compensation, green is a whole mechanism. There is a lot of noises are present. That's why it is like looking clumsy. So we can think like predicted measurement compensation is more accurate than the whole mechanism. And similar way we have done for control to actuate and reflection also. So we are using control laws U is equal to K and K exact. This exact K given K is filter state of filter state. So this is what we have feedback. And after compiling all those models, and we are end up with first 9 and 10 equations. First one is a state equation. It is an augmented state equation. Another is augmented measurement equation. So here from the many literatures they have done with the whole mechanism. So they won't be this F tilde exact K given and G tilde exact K given. So these information will be there. So this is the variation. If you are using any predicted compensation, this is the variation. So accordingly, based on this A tilde, F tilde, gamma tilde, all are like augmented matrices only. So this is this A tilde, A1 to A7, A8, and gammas F. These are all belongs to this A tilde, B, F tilde, gamma tilde, these things. And then coming to estimator, we are doing estimation through projection principles. So first prediction phase and updation phase. In that prediction phase, first one we have a predicted state information. The next one is a predicted gain and prediction covariance. In updation phase, we'll have filter state, filter gain, and filter error covariance. So based on this innovation below, innovation is there, y minus y hat K given K minus 1. It's a deviation between actual measurement and the predicted measurement. This is what I keep on update. So the developed estimator is suitable for online computation because E is only information. This innovation error will keep on changing. Based on this one, entire thing will get changed. So this is the major computation burden of this algorithm. So these are all like what we had. So in this equation, so everything explained detailed here. And last one is measurement error covariance. So here we are using some centralized diffusion estimation. That's why we have connected directly. We are using those things. And this based on this error covariance, we can go for some distributed fusion estimator type. And one more thing is this second order moment. This is we will be having expectation of x of k plus 1 and x of k plus 1 transpose. So after doing arithmetic operation, we'll have this equation. So here also we have one more specific term, that f bar pk given k minus 1 f bar transpose. Because our augmented state vector have predicted information, that's why we end up with that equation. And the controller design based on this Lyapunov equation, Lyapunov function vk is equal to x transpose px, and delayed state information. So based on this Lyapunov function, we are ending with the 27th equation. So we are solving through LMA and we are getting the results. So the same approach only. Based on actually the 27th equation, we have bilinear matrix inequality. So we just want to convert linear matrix inequality. For that, we are using some separation principle for that. About the discussion, predicted compensation we are using so that we can have a better response of our system, even though if we are not receiving any measurement. And centralized fusion estimation can handle everything. And if even various for each and every sensor will have a various probabilities for transferring a data. So for that also it is suitable. And with the help of event triggered mechanism, energy utilization for the entire entire running system, it will get reduced. And computation burden also we can reduce through prediction measurement compensation. And it is suitable for noisy process. So coming to benefit, it is suitable for multivariable systems and power consumption we can reduce a lot. So this is what. Thank you. Having.
Thank you, Senthil and Srinivasan. We have time for a couple of questions. Yes.
All right, thank you for the presentation. I have a couple of questions. So first question is about your delay. So how you decide? I note there's equation -1, and then there's a 2. Is I think it's a prediction horizon. So how you decide for your own case? So is it always -1, or is there any general suggestion for that? Or another question. So you talk about cyberspace, right?
Yeah.
Physical space. How many nodes in your data pooling from the instrument? So is just one instrument or one sensors, or there's a multiple? Then you will like average it, or can you elaborate on that? Thank you.
Multiple data pooling we can use because we are using separate channel for each and every machine. That's fine. And this delay, it can happen. Not always it can happen. We cannot say. But always we are looking for on-time arrival of data. So after sampling, I need data. So that's what we are expecting. For such a case, there is a possibility of delay and loss due to like processing delay, and there is a possibility of data traffic also, network traffic. So that time we will not receive any data. So for that only we need some compensation. And delayed in since half of the sampling time we can accept because for computation time we need at least that much time. And for loss, if it is more than the delay time, we can consider loss. So
I think there was also a question on how you choose the prediction horizon.
Prediction.
So actually I can summarize. Actually every loop has some delay is maximum delay is allowed. Okay, beyond that we will consider as a loss. Okay, it's maybe 1 millisecond or something. Okay, so every local control unit. Okay, and coming to your prediction horizon question, we have not incorporated any on more predictive scale. So that concept is not applicable here. Okay, because it's not a MPC framework. It's like the solving on that. Okay.
So it doesn't have to be an MPC problem. I think because you are predicting, the question is whether you are predicting one step ahead.
One step, naturally.
I think that's the
we are not going for more than one. Okay, so one step prediction only. If suppose that information is not available, your model can feed the data. That's one of the concepts. And in order for a power management, we have incorporated event triggering mechanism. Okay, so the naturally what will happen once it reaches a steady state, there is no need every time fetches the information. Okay, we can use what happened here last time. Okay, that's the main concept. Thank you.
Thank you. Any quick question? I just had a very quick question. So you said that there is provision to handle sensor data and transfer probabilities. Has it been tried out, or it's only a kind of an on-paper speculation?
Actually, we have tried out not adapting with exact results. So, based on some multiple times we are collecting a data with timestamp information. So, from there we can understand how many data can have delay or how many data can lost for the particular channel. So, based on that we can calculate the probability. That's what we are doing now. But still, we need more data. More and more times we need to.
But if you know the probabilities a priori, can you incorporate? That's the question.
Assumptions.
Yeah.
Probability now we are doing some assumption, but if you know probability, then only this is suitable. Otherwise, we can go if we don't have any data instead of going for probability. General Kalman filter with some condition it is useful.
Right. Okay, so let's thank the speakers once again for a nice presentation. Thank you.